there are basically three things that I want to tell you just a few words about. The first is some of the work we do on basic climate science, climate impacts. The second concerns the Intergovernmental Panel on Climate Change and our work in coordinating the Working Group 2 agenda, deals with impacts, adaptation, and vulnerability. Kate will talk to you mostly about that. And the third thing is experimental studies of climate change that occur especially at Jasper Ridge, and I'll have a chance to show some of you the details of that work as we get out there later this afternoon. But what I'm going to focus on in my comments here is sort of where we are with basic climate science, with a framing about the things we know now and the things we most need to know in the future in order to make good decisions. When I think about climate science, I think about avoiding the situation that Tom Tolles, who's a wonderful science communicator, describes in this cartoon, in which he's describing the next breakthrough in 2060 being that we really should have done things differently in 2010 than we did. And at least for me, that's the real policy-relevant challenge that we face in climate science today, is how to make sure that we have the information we need and that we take the best possible advantage of that information in order to make good decisions. So let me start with Article 2 of the UN Framework Convention on Climate Change. This is basically what is the current operating international legislative document that says what the issue is and what we as a global community have decided to do about it. You may disagree with whether the global integrated approach is the best one, but there are really two components of the UNFCCC Article 2 that I want to highlight as underlining the key issues for today. The first is that the goal is to prevent dangerous anthropogenic interference with the climate system. What is dangerous? When does it occur? Have we already passed a point where climate change is dangerous for some particular stakeholders? Is there a way that we can come up with a general definition of what's dangerous and what's not? The second criterion that's really important is one that's related to velocity, not only the velocity of climate changes, but the velocity of societal responses. And the wording of Article 2 says, within a time frame sufficient to allow ecosystems to adapt naturally to climate change, to ensure that food production is not threatened. And so the key focus of what we're trying to do is to protect natural ecosystems and to protect food security. And then finally, a really interesting and essentially two-edged statement about sustainable economic development. It says, and to enable economic development to proceed in a sustainable manner. What's so interesting about this statement is that on the one hand, it means we need to take action such that climate change doesn't erode opportunities for sustainable economic development in the future. But on the other hand, we need to make sure we don't spend so much addressing climate change that that spending erodes opportunities for sustainable economic development. So it really defines what I think of as a tightrope that we need to figure out how to walk. In order to do that, I think it's absolutely critical that we think about framing responses to climate change as a challenge in managing risk. And formally, we define risk as the product of two things, the probability of some event happening and its consequence. It's useful to think of a metaphor here. Jim Hansen, great climate scientist with NASA, talks about climate change as loading the dice on future outcomes. And the more the climate changes, the more we emit greenhouse gases into the atmosphere, the more likely we are to come up with unfavorable combinations on the dice, where there are extreme events, unacceptably high temperatures, a failure of infrastructure. John Holdren, the president's science advisor, likes to use a metaphor about with climate change, we're basically in a car that's driving in a fog with a cliff out there someplace. Sometimes it's night, sometimes the car's lights don't work. We know that cliff's out there someplace, but how are we going to manage risks and manage expectations to keep from driving over that cliff? I want to spend just a couple of minutes on a slightly more extended, but I think more useful metaphor. And I think about the world economy as essentially a a truck that's headed down the freeway of life. And this truck is producing lots of good things, but as a consequence of the way its energy system runs, it's dumping nails on the road. And following vehicles have to deal with these nails on the road. With just a few nails, this is not that big a problem. If you've got really great tires or anti-lock braking, it's not that big a problem. But if you've got bald tires, if there's really heavy traffic, if it's raining, these nails on the road get to be a real problem. And as there get to be more and more nails, we move beyond the occasional flat tire to the risk of a car spinning out. And the more nails there are, the more cars there are, the more risks there are of really catastrophic multi-car collisions that bring the whole highway to a halt. And part of the reason I like this metaphor is it captures the essential nature of climate change as being an unintended consequence of activity that's producing a lot of good things. And it also is useful because it highlights the three essential things that we can do about climate change. We can adapt, we can buy beefier tires, or we can lower the speed limit. We can mitigate, we can slow the rate at which we dump the nails on the road. Or we can deploy a strategy that's often called geoengineering, which is masking the problem. I think of that as like spreading a piece of paper over the nails on the road so that the next car may not hit the nails, but the nails are still there and succeeding cars are going to run into them. When we think about climate change in this way as a problem in managing risks, it introduces a whole bunch of interesting and useful opportunities. Let me dwell a little bit more on this idea of defining climate change as a problem of managing risk. So let's look at some outcome. It has probability that's normally distributed with some central tendency. Mostly we tend to know about the central tendencies with climate change, and we're relatively bad at describing the full probability density function. With lots of impacts, the impact tends to increase more or less exponentially as the amount of climate change gets to be greater. And if we define risk as the probability of those two, shown with the probability in the green here, you can see that you end up with a maximum of risk, which isn't necessarily at the same point as the greatest probability of climate change. This is a consequence of the exponential increase in the consequences as the change get to be bigger and bigger. So when we think about managing this, we really need to know what that full probability distribution looks like, and we need to know what the shape of the response of the consequence to the climate forcing is. One of the interesting consequences and important consequences of dealing with climate change as a problem in risk management is that knowing less is typically not a good motivation for not acting. If the amount of risk is the motivation for action, you can see in this example here, I've simply increased the standard deviation on the normal distribution, that the risk increases dramatically as you go to higher levels, just because we haven't constrained the uncertainty as much. So at least formally, knowing less increases the motivation for action. Let me give one example to conclude in my few minutes here. In order to take effective action on climate change, we really need to know and deeply consider its special features. There are really 6 that I think are important. The first is that it's gradual, onset's delayed. We're talking about actions now to prevent or delay effects many decades in the future. It occurs against a lot of background variability so that it's hard to detect and even harder to attribute trends. The impacts tend to be permanent. A wide number of papers over the last couple of years have indicated that in the absence of human actions to deliberately remove CO2 from the atmosphere, climate changes persist on a millennial timescale. The impacts are global. Emissions in the US influence the whole world, but the impacts are differentiated. There is a big contrast between historical and future responsibility with the developed countries in the northern hemisphere responsible for most of the historical emissions, and developing countries responsible for likely most of the future emissions. And then finally, there's a big difference between who emits and who tends to be most vulnerable. And in general, the people who are most vulnerable to impacts of climate change are those who are poor, who have poor access to advanced technology and infrastructure, who are elderly or ill, or who are in situations with poor governance. There's no doubt that climate's warmed. In 2007, the IPCC concluded that warming of the climate system is unequivocal. Nobody really debates debates this. And, you know, we've really understood the basic physics behind climate for a long time. This is the cover page of a 1896 paper by a brilliant Swedish chemist, Svante Arrhenius. And in 1896, Arrhenius knew that emitting more CO2 to the atmosphere would warm the climate. He knew that a warmer atmosphere would encourage evaporation and that the warmer air would hold more water vapor and that water vapor would amplify the warming from CO2. And Arrhenius knew that some of the CO2 would partition into the ocean and some would stay in the atmosphere. He was able to calculate a sensitivity of the climate system to global warming that's slightly higher than the range we talk about now, but overlapping with it. And since 1896, when Arrhenius published these conclusions, essentially no one has debated any of the underlying mechanisms. All of the debate in climate science is about the magnitude of the feedbacks that either amplify the effect of the forcing by greenhouse gases or that suppress it. And what I'd like to conclude with is an example of some recent research from my lab that takes advantage of a wide range of data to provide additional new insight over what this sensitivity is. And this is a study of the intrinsic sensitivity of the climate system to forcing by CO2. And the normal thing that people talk about is how much does the average temperature warm if you double the CO2 concentration from P-industrial. This is work from a PhD student who finished in 2010, Carolyn Snyder, who's now the Director of Climate Services for the state of Delaware. The IPCC uses a wide range of approaches to diagnose climate sensitivity. The likely range they identify as 2 to 4.5 C, and concluded in their 2007 report that a sensitivity higher than 4.5 C cannot be excluded. IPCC likes carefully calibrated uncertainty language, and this is a little bit disconcerting. But you can see that all the models cluster from 2 to 4.5 with a most likely value at 3C. 3C warmer if we double CO2 from pre-industrial. Carolyn was able to take advantage of a wide range of paleo records, including records from the tropics, which had not been included in earlier assessments. And with this very wide range, was able to get a new measure of sensitivity, a 4.1 degree, and to constrain that in a very nice way, given the very large number of data points that were available. Carolyn's estimate is shown in the black curve here, and you can see that the most likely value is now shifted up almost a third from the IPCC most likely value. It appears that the reason the IPCC got it wrong is that climate sensitivity in cold periods, shown with the blue dashed line, is a little bit lower than it is in the hot periods, shown in the red dashed line, and we're now very much in a hot period. The good news from this study is that it's very unlikely that climate sensitivity is higher than about 6C, but 6C is a world that is just fundamentally different than the world we live in now. So I think this is important results for kind of framing the climate issue, for putting us in the context of managing risk, but it also highlights the kind of progress we can make in terms of defining these probabilities and as a next challenge, defining the consequences that accrue. So I want to conclude just by kind of returning to the framing of climate change as a problem in risk management, where we've got probability, consequence, and the product, and leave you with a thought that further progress depends on two critical things. The first is accurately characterizing the probability distribution of various kinds of climate changes, not settling for just knowing the most likely outcome, and also accurately characterizing the sensitivity of a wide range of impacts to climate change, especially in the context of multiple interacting stresses. It's a big challenge, but it's one where we have a wide range of tools, and it's one that I hope many of you will join us in the future. Thanks very much.